Welcome to the how-to video for the complete communication system decibel and power analysis. Okay, here's our system. We have a 100-watt transmitter, 150 megahertz, 35 feet of RG58 coax, a 2M7X Yagi antenna. We have 20 kilometers and 100 megahertz signal through air, received by a antenna 2M4X, 50 feet of RG58AU coax, and received by our receiver here. And we're looking for coax losses, free air losses, our ERP, and our antenna gains. And then at our receiver, we're going to do dBm and microvolts. First thing we're going to do is take a look at our coax attenuation chart. And we're going to look at our RG58AU at 150 megahertz. And we come up with, at 35 feet, and it's a ratio, 2.135 dB. And our receive cable at 3.05 dB. Alright, let's take this time to look at some antenna definitions. We have an isotropic radiator. It's a theoretical antenna that radiates waves with equal intensity in all directions. Actual antenna doesn't do that. Next one would be dBd, decibels relative to a dipole. So measures the gain of antenna concerning a reference dipole antenna. A reference dipole antenna provides a fixed 2.15 dB of gain over an isotropic antenna. Dipole antennas consisting of two conductive elements are fundamental elements in RF engineering. And then we look at dBi, decibels relative to isotropic. It's a unit measurement that describes how much power an antenna transmits in a single direction when compared to an isotropic radiator, which transmits in all directions at once. Okay, let's take a look at our 2M7X antenna specs. We're interested in the 12.3 dBi, the gain of the antenna, and in order to convert dBi to dBd, we need to subtract 2.4. And we need to double check our frequency, and it's 144 to 141 megahertz. Okay, here's our receiving antenna, and we're looking at 9.6 dBi. And it's already in dBi, so that works for us. Okay, in order to calculate our free space path loss, we need to go to this link here and utilize their calculator. So here we have our distance of 20 kilometers, 150 megahertz, our transmitting antenna gain, and our receiving antenna gain, and we push calculate. And our free space loss is 80.1 dB. The next thing we need to do is calculate our effective radiated power, ERP. And we're going to go to this link here. And we're going to put in our transmitter power, our system losses to the antenna, which is our coax, and our antenna gain. It's actually 9, but it's maximum of 6, so we're just going to go ahead and stick with that, and we're going to go to calculate, and we're going to come up with 54 dBm, or 251.2 watts. Okay, we have the formula here, and we have 100 watts based on 1 milliwatt. So I'm going to go ahead and use a calculator. So we're going to do on clear log 100 divided by 1 second EE minus 3, don't use the minus sign. Let's close the parentheses, equals times 10 equals, and that should give us 50 dBm. Here I've taken all of our calculations and put them together, and the beauty of decibels is we could just add them and subtract them. Okay, let's calculate our transmitter dBm input. 28.5 so dB. We're going to go through and I put that chart into our take equation. A look and add everything up. So we have 37.7 dBm from an amplifier. Steps. Our cable attenuation coming out of our amplifier is 2. Here's our complete system dB. With all our ERP the answers plus 54.1 dB. This here for you to look at. We lost our free air loss is minus 80.1 dB. Our antenna gain going into our receiver is plus 9.6 dB, and our cable attenuation going into our receiver is minus 3 dB, and we come up with 16.2 dBm.